Hello and welcome to another video of Grokking the Coding Interview series in which we are going through the breadth first search approach at the moment. And in this video, we'll have a look at the minimum depth of a binary tree, which is classified as an easy problem. So let's quickly try to understand what do we mean by minimum depth of a binary tree. So essentially, we are looking for the shortest path from the root node until the nearest leaf node. And we have a couple of examples here. The first one being this one, where we have root as 1. We are looking for the leaf node, which happens to be 3. And if we calculate the length of this path, it will be 2. We have another example here where we start at the root node and the leaf node, or the closest leaf node is here. The length of this path is 3. And our minimum depth in this case will be 3 as well. So we get a sense of what do we mean by minimum depth. So what is our approach at this point? Like, how are we thinking of solving this problem? So essentially, what I'm thinking at this point is we do the level over order traversal, which we have been doing for other problems as well. If you have not checked it out, please go ahead and like have look at the previous approach where we go through the level order traversal and other approaches where we use queue as a data structure in order to accomplish that. So essentially what we want to do is we want to do level order traversal, go through this tree level by level, and as soon as we encounter a node in that process which does not have a left and the right subchild, or left and the right subtree, it would mean that we have encountered a leaf node. And at that point, we are good to return the depth we have for that level of the tree. So let's quickly try to see what how we can implement the solution here. As a first step, from collections, we want to import dq, which will enable us to use the data structure queue. If root is none, we simply return 0. We initialize the queue using the dq. We will append the root here, and we will iterate through, or we'll continue to run the while loop until the queue is empty. And at this point, we want, of course, the level size, which will be the number of elements we want to look at that level. So it will be the length of the queue. We are only keeping level wise elements in the queue. We also want to have a min depth, which will be initialized to 1. If you remember, the root node, so I mean, if you see here, the root node in itself uh, contributes towards that length of the path. So we'll start at 1, and this we initialize to 1, which is good. And at this point, we are good to start traversing. Level size, we get the current node pop left, q dot pop left. Okay, so what do we want to do? We want to be careful that if the current node left, if not current node left, and not current node right, then we simply want to return the min depth. Essentially, if the current node is not having a left or the right subtree, it's a leaf node, and we are good to return the depth of the tree at the moment. If current node dot left, then we append it in the queue. If the current node's right, then we append it into the queue as well. And we want to, outside of the for loop, we want to increment the min depth as well. And in the end, we want to return the min depth again. So let's quickly go through the implementation, see if in case we are missing anything, we'll try to run and see if our answer is correct. And then we'll directly hop into the space and time complexity of the implementation. Okay, so if there isn't any root, we simply return 0. This is the base case. We initialize a queue, we append the root, we have min length equals to 1. While the queue is not empty, we get the number of nodes we want to look at for that level. We iterate, we extract a node. If both the left and the right subtrees are absent for that node, we simply return the min depth. We know that this is a leaf node. If otherwise, we go ahead and see if the left subtree is there, we'll append it into the queue. If the right subtree is there, we'll append it into the queue as well. And we keep incrementing the min depth outside of the for loop. This should give us the answer which we are looking for. So let's try running it and see if we have made any mistakes here. So the tree minimum depth, let's see what the tree is. 12, 7, 1, 10, 5. 12, 7, 1, 10, 5. So here we have minimum depth of 2. And then we also add 9 and 11 in here. We add 9 and 11, and here the minimum depth is 3. So again, it will be 3. So I think it'll be a good point to speak about the space and time complexity of this implementation, specifically the worst case scenarios. So if in the worst case scenario, it can happen that we have no leaf nodes. In the worst case scenario, that it can happen that the leaf nodes are in the final level of the tree, hence we'll have to traverse pretty much all the nodes. So the runtime essentially will be O of n in that case. And when it comes to the space complexity, I think we have a queue element here, which can be n by 2, so O of n at max. And yeah, so pretty much O of n will be the space complexity as well. Let's quickly jump in and see uh, what their space and time complexity is. Yeah, which is in line with how we have approached this problem. So I hope you found the explanation clear. Please let me know in case something was not clear or if you want me to elaborate on something else. Until the next video, have a great day.